The interstellar object Oumuamua is marked with a blue circle near the center of this picture, which was created using multiple images from the Gemini South Telescope and the Very Large Telescope. Credit Meech al. ESO, our solar system's first known visitor from another star. The recently discovered object, called Oumuamua, could be a bonanza for researchers. With only a brief window of time to observe the cigar-shaped wanderer before it zooms beyond the reach of our best telescopes, astronomers have crammed in observations with the hopes of learning more about this interstellar interloper. Not only is the fast-moving object intriguing in its own right, it may also provide insights about how planetary systems evolve. Oumuamua caught the eyes of astronomers on October 19 this year. Calculations revealed the space rock was traveling at 26 km per second relative to the Sun, a rapid clip that, along with its extremely elongated orbital trajectory, suggested it came from outside the solar system. Telescopes swiftly targeted the object, with most researchers expecting to see a cometary tail trailing from an icy visitor as it approached the Sun. But to their surprise, Oumuamua showed none. Instead, it looked more like an asteroid. It does not resemble a comet. It had no tail whatsoever, says Karen Meech, who studies comets at the University of Hawaii at Manoa. Meech used NASA's Hubble Space Telescope and other observatories to examine the mysteriously inert space tourist asteroid. A comet, why does it matter? The answer ties into our understanding of how planetary systems grow over time in their natal protoplanetary disks around young stars. Newborn giant planets can jostle one another, using their gravity to push each other around. They also lord their size over their smaller neighboring worlds, and especially over the kilometer-scale objects called planetesimals left behind as debris from the planet-forming process. When a giant planet throws its weight around, more than half of these planetesimals can wind up hurled from the system. Because most of a typical protoplanetary disk is icy, in 2016 Meech used solar system observations to estimate there were as many as 10,000 icy objects for every rocky object. Icy objects should dominate the ejector. Location also makes a difference in what gets thrown out. Most gas giants lie on the other side of the snowline, a demarcation in a protoplanetary disk where its composition shifts from mostly rock to mostly ice. Objects on the star side are baked dry by starlight and thus predominantly rocky, whereas objects on the darker outer side are colder and tend to retain more ice. In our solar system, the snowline lies between the orbits of Mars and Jupiter, and astronomers believe that distance is roughly where it started out for other Sun-like stars. As outlying gas giants shift their orbits, they become more likely to interact with nearby ices than the more distant rocky material closer into the star, adding fuel to the idea that most of the interstellar visitors we observe should be icy, including Oumuamua. The population of planetesimals floating in space should be dominated by comets, not by asteroids, says Sean Raymond, an astronomer at the Laboratory of Astrophysics of Bordeaux in France who models the early solar system. In a recent paper, Raymond argues the extrasolar visitor is more like a defunct comet than an asteroid, based on how the exoplanets we've observed so far are laid out. It's kind of weird that this object Oumuamua doesn't have any signs of activity. Oumuamua's oddball spin could be related to its origins as well. According to new research posted on the preprint server arxiv.org, the visitor is tumbling willy-nilly rather than smoothly rotating on its axis. The researchers, who declined to comment due to embargo concerns, state in their paper Oumuamua was likely set tumbling within its parent planetary system, and will remain tumbling well after it has left. Oumuamua's motion, they speculate, could be due to a long Argo collision with another body at the extreme tidal torquing it may have experienced during its ejection from its parent planetary system. Alternatively, its spin could come from the jet-like outgassing of icy material vaporizing in sunlight, the process that creates a cometary tail. But, again, the object did not appear to sprout a tail when it closely approached our Sun. If indeed Oumuamua is an icy body, how did it avoid growing a cometary tail? David Jewett, an astronomer at the University of California, Los Angeles, suspects any ice might be buried under a layer of material damaged by the charged particles known as cosmic rays that bombarded Oumuamua while it traveled through space. The prolonged exposure will toast the surface, forming a protective crust, he says. A crust of only half a meter could be enough to shield the ice, Jewett adds. He calculated how heat could have moved through the object using solar system analogs because its surface composition is unknown, and found it would not make it very far. You'd only have to go a meter or two into the surface, he says, to reach the interstellar temperature, which is only a few degrees above absolute zero. Not everyone thinks Oumuamua could be a crusty comet. I would not expect that volatiles would be sealed up in any particular way, Meach notes. David Trilling, who studies asteroids at Northern Arizona University, says that although it is possible to strongly irradiate primitive material in the solar system, it's not obvious that you can get that irradiated goop on an interstellar object. Unfortunately, we are unlikely to ever know what materials comprise Oumuamua because it is moving far too fast on its way out of the solar system for us to have a realistic chance of catching up to it with even our speediest spacecraft. But it left astronomers excited about the next one. They anticipate spotting about one interstellar visitor a year in the near future. If those objects all wind up being rocky, that could mean bad news for our understanding of planet formation. If the first 10 objects were all rocky, then it would mean we're really off on something important, Raymond says. Most likely, it would mean the rocky material makes up a far larger portion of the natal disks than expected by the models. We'd have to be way off on where planetesimals form, he says. In a separate paper, UC Santa Cruz astrophysicist Greg Laughlin estimates that an abundance of rocky interstellar voyages would require about 200 Earth masses of debris to be ejected from every planet-hosting star, rather than the 10 Earth masses current models call for. It just doesn't really work, he says. It's just a little too much to ask for. If Oumuamua is icy, Laughlin thinks it has important implications for Neptune-size worlds in the outer reaches of other planetary systems, which have been a challenge to observe. Because distant Jupiter-size worlds are only found around roughly 1 out of every 10 stars, he thinks the ejection of Oumuamua-like objects might need a boost from an as-yet undiscovered population of icy Neptune-like worlds in Jupiter-free systems. For now, scientists are waiting for the more tourists from other solar systems to visit, hoping long tails behind them. It's not hopeless, Jewett says. We just have to wait for the next 10 or so to be discovered. If none look like a comet, that would be interesting. It would tell us a little more than just seeing one object. This article was first published at scientificamerican.com. Copyright scientificamerican.com. All rights reserved. Follow Scientific American on Twitter at Siam and at Siam Blogs. Visit scientificamerican.com for the latest in science, health and technology news.